Good evening, everyone, and a very warm welcome to the sixth session of our webinar on Cellular Automata. Now, we have created a channel in YouTube where you can find all the videos of our previous sessions. So, if you are interested, please subscribe to that channel. And like always, let me first announce the event details of our next webinar. Our next webinar is scheduled on 9th of January at 7 p.m. Indian Standard Time, where Professor Zenil Martinez from National Polytechnic Institute, Mexico City, USA, will talk about ambiguity and computability in complex cellular automata. Now let's start today's session. Today we are delighted to have among us JAM, Professor R. Ramanujam from IIST Chennai, who will talk about Presburger arithmetic, automatic sequences, and linear cellular automata. Although our eminent beloved speaker needs no introduction, but for the sake of the program, let me introduce him a little. Professor R. Ramanujam, fondly known as JAM, is a professor in the Theoretical Computer Science Research Group in the Institute of Mathematical Science, Chennai. He got his BE in Electrical and Electronics Engineering from BITS Pilani and his PhD in Computer Science from Tata Institute of Fundamental Research, Mumbai. After postdoctoral research at the City University of New York, he joined the Institute of Mathematical Science, Chennai, as faculty in 1987. His research interests are mathematical and philosophical logic in computer science and theory of computation, and their applications to theory of distributed systems, game theory, and security theory. His other research interests include temporal logics and verification, partial order models of concurrency, and logics of knowledge. He was the Lawrence Fellow of the Royal Netherlands Academy of Science at the Netherlands Institute of Advanced Studies. He is actively involved in the Indian Association for Research in Computing Science and the Association for Logic in India. Also, he has another identity. He is an activist. He has been associated with the Tamil Nadu Science Forum since 1990, and his active involvement includes in science popularization and school education. He is the editor of Thule, a monthly science magazine for children. He was a member of the Yashpal committee that formulated the National Curriculum Framework in 2005 and chaired the National Focus Group of Teaching of Mathematics NCERT. Currently, he is the Vice President of Mathematics Teachers Association of India and member of the Core Committee of CH Pathshala, an Asian India initiative. He is also one of the initiators of the Indian Scientists' Response to COVID-19 ISRC, which started as a group of Indian scientists who came together voluntarily in response to COVID-19 pandemic. For people who may not know about this, ISRC is the leading forum that has been working to support evidence-based action by national, state, and local governments through data analysis and modeling from a scientific perspective, provide accurate science-based resource for activist group working on the ground, and to mobilize the academic community, including students at all levels, to participate in science communication and local action, to act scientific interpreters for the public at large. So this group is, although it started initially as a couple of people, now it includes more than 500 students, scientists, researchers from all over the India, and also from some Indian scientists from laboratories all over the world. So we are very glad that he accepted our invitation to talk.
Okay. Thank you so much for that very kind introduction, Kamalika. Can you hear me?
Yes.
Is the audio okay? Yeah, please tell me if there is any problem. We'll start presenting. Yeah. So I hope you can see the screen. Very good. And yeah, it's a pleasure for me to talk in this seminar. Well, when I say pleasure, I should also express my apprehension, because I hope what I am saying will be of interest to everyone. So thanks very much to Sukanta and Kamalika for this invitation. Do feel free to interrupt at any time, and I welcome any comments, questions, or any interruptions at all. It's much better to talk to people than looking at my screen. Unfortunately, this is what we have all come to during this pandemic. So there is a statutory warning. The talk has only a thin relevance to cellular automata, but I still hope some of these ideas will interest you. The talk is mainly on logic and automata theory. I know that this group has, I can see among the audience, very eminent cellular automata specialists. And what I have to say is generally on automata theory and logic. And I hope these connections will be of interest to people. Okay, so the summary of what I want to ask is this. The main question is, can we get decision procedures for properties of evolution patterns of linear cellular automata? Now, the thing is that this seems like a stupid question to ask, because cellular automata, Turing complete, almost any non-trivial property is undecidable. There is Rice's theorem, so what do you expect, right? Now, so the answer is quite unclear, but there is at least one interesting direction for research that I want to talk about. And the idea is that we can hope to characterize some of the sequences generated by, at least in the context of one-dimensional linear cellular automata, as automatic sequences. And then once you have automatic sequences, we can use Presburger arithmetic, which is a decidable theory, and we can use it to reason about such sequences. Now, this is widely speculative, but I hope to show at least one very, very nice theorem which shows that at least in one case, people are able to do this very effectively and very well. So, and it's in a way that opens up so many interesting questions of interest to additive number theory, and with many interesting applications. Okay. So this is what I want to talk about. So we're not going to see much of cellular automata, but we're going to see mainly automatic sequences. And I hope the relation between the two will be of sufficient interest. So now, there are lots of fascinating problems in additive number theory. The most famous theorem of Lagrange says every natural number is the sum of 4 squares. I think we've all read this at some point. Goldbach conjecture, right? Every even number greater than 4 is the sum of 2 primes. And then the Waring's problem. Right? Again, all around that time, right? 18th century questions. Every natural number is the sum of 4 squares, 9 cubes, 19 fourth powers, and so forth. I mean, I was in fact tempted to show the quotation from Waring in Latin. It's a complicated sentence, but it's really interesting. He just says, etc., right? And it took more than 2 centuries of research to settle these questions. Hilbert was the one who proved that Waring's problem in general for when you're looking at fifth powers and more is decidable, gave a characterization, but then the numbers, and this 19, the sum of 4 squares was settled soon, 9 cubes took some time, and 19 was actually settled in early 1980s by my colleague and friend R. Balasubramanian, who was our from math science, and de Jouvier and some French mathematicians. So it's as late as 1982, I think. Yeah, 82 or 84, I don't remember. Yeah. So this is a very colorful history. Now, so additive number theory has many problems of this kind, which are naturally stated as sums of. So the general kind of problems that people look at is if you take a subset of natural numbers, right? Assume that 0 is in it, and you say that S is a basis of order H if every natural number can be written as the sum of H elements of S, not necessarily distinct. Like we talked about squares, right? And then you say sum of 4 squares. So that's, squares form a basis and order 4. So this is the general kind of question. And you say S is said to be an asymptotic basis of order H if every sufficiently large natural number can be written as the sum of H elements. Sorry about that lack of space there, not necessarily distinct. Now, and the search for additive basis of this kind has led to really beautiful mathematics, over a couple of 100 years. What kind of sets can form additive basis for natural numbers, right? Now, here is one example that I like. A number is said to be an OOPS number, okay, if it has ones in all odd-numbered positions of its binary representation. Sorry, there is a break there, where the most significant digit is in position 1. So basically what you take a binary representation of a number, and in all odd positions, it should have 1. Then such a number is called an OOPS number. So, and then if you sit and work out, you will find that 1, 2, 3, 5, 7, 10, 11, 14, these are all the first few OOPS numbers. Now, the density of OOPS is roughly square root n, and which is sufficiently high, at least square root theta, I should put theta root n. So it's sufficiently high to make it a candidate for a basis. And in fact, the theorem is that the OOPS numbers form an asymptotic additive base of order 3. That is, if you take any sufficiently large number, it can be written as a sum of OOPS 3 OOPS numbers. And theorem also says that you can't do it with 2. Okay. Now, those are the kind of theorems that are proved. Yes? Any question? Okay, I'll continue. So, sorry. Yeah. So, why am I mentioning this? Because it turns out that looking for new bases, right? And it's not incidental that I brought in the binary representation of these numbers. So the idea is that you start looking at it in a particular base, you can start thinking of those numbers as words over some finite alphabet. So in this particular case, I'm thinking of these numbers as strings over 0, 1. And this actually, you can go from this kind of additive number theory to automata via logic. There's a remarkable theorem due to Buchy and Veronique Brouillet in Paris, that it says that every first order statement in the theory of order addition about a sequence, in any such statement about such first order sequences, if it happens to be defined by a finite state automaton in base k, that is decidable. Now, we have to unpack the statement. What does it mean? And now, I'm not going to define first order logic. When I write F4 sigma, what I'm saying is that you have some unary predicate. So if, let's say, sigma is ABC, you have unary predicates PA, PB, PC, etc. So you can say the exit position in the string is labeled A, right? So the first order variables, X, Y, etc., denote positions in the string. And then you can talk about addition. So you can say the xth position has labeled A, yth position is labeled B, then x plus yth position is labeled C, etc., etc. So this is kind of thing that you can play around with. So you have x less than y. So it's basically the first order theory of linear order enriched with addition. And the point is that these formulas define their models or sequences, and if as I said, base k. Let's stick to base 2. I mean, almost everything that I'm going to say, binary is all that I need. And as long as that sequence, that is what you call an automatic sequence. So if that sequence is generated by a finite state automaton, then you can check whether that statement is true or false. Now, this is originally Buchy's theorem, but there was some error in the way Buchy formulated Veronique-Breuer fixed it, and then subsequently many people have taken up this theory and developed it. Now, the main point is that there is an automaton recognizing these inputs corresponding to values of the free variables that make the statement true. So if you have n free variables in the formula, you have the automaton runs over n tuples of these sequences. So now you can show that the OOPS numbers are recognized by a simple deterministic finite state automaton, which takes their binary representation as input. And that's a route to the proof. The proof that earlier I was mentioning, that this theorem that the OOPS numbers form an asymptotic additive basis of order 3, and this entire proof can be done automata theoretically. Now, so it gives the point is that additive number theory, the kind of tools that are used are very different, and this goes principally into analytic number theory. Huge amount of work has been done in 200 years plus more, and automata theory brings in a very different look, and the kind of additive basis that have been that people have come up with using automata theoretic techniques, gives a completely new light into these, and so that's something very, very interesting. So this is the kind of connection that I want to talk about. Now, I don't have a lot to say. I can go over the proofs in detail for people interested, but first I want to give the basic ideas and the kind of connections that I'm talking about. Any questions so far? Okay. So, in the first order theory, you can write things like sums of two numbers. There exists x and y such that n equals x plus y, and oops x equals 1 and oops y equals 1. And, these are very easy functions and to write in first order logic, extracting the first breakdown. And from there, I can take you to, once you realize that you can talk about n-tuple, I'll give you the definition later as we go along, that once you talk about numbers as sequences that automata can recognize, then there are interesting theorems, and these are very recent theorems. This is one due to Bell, Hare, and Shalit, 2017. If a set of natural numbers is recognized in base k by a finite automaton of n states, then it is decidable if S forms an additive basis or an asymptotic additive basis of finite order. So this is already a remarkable result, which we could not have even guessed at by the traditional methods of additive number theory. And then they go on to prove that if S is a basis, there is in fact a computable bound on the order of the basis. I mean, you can actually compute the order of the basis. The order of the basis, remember, is that, like for instance, in the case in Lagrange's theorem, order is 4. You're writing it as a sum of 4 numbers. In OOPS numbers, the order is 3, right? You can write it as a sum of 3 OOPS numbers and so on, right? And in fact, the minimal order that, like I said, it's 3 but not 2. The minimal order for OOPS is 3, right? That's in fact something that is computable. And so what kind of methods are, I mean, I'm not going to talk about the proof of this theorem because that is not as important to us, but what kind of methods go into proving these kind of results? There are many interesting results that I can refer. Lots of interesting results in recent times. The 3 that I have picked are all in the last 5 years, right? Banks, 2015. Every natural number is the sum of at most 49 base 10 palindromes. What's a palindrome? It's a word that's identical when you read it left to right or right to left, right? Malayalam is a palindrome, for instance, right? And so base 10 palindromes is what we are interested in decimals. And this is a theorem that amazingly, additive number theory is very much like a Lagrange's theorem, and it's a very recent theorem, right? And here is another. For all bases b greater than or equal to 5, every natural number is the sum of 3 base b palindromes. This is by, and then Charlotte's. And by the way, a lot of the ideas that I'm presenting is follows Jeff Charlotte's work. Jeff Charlotte's presentation style, his papers is what I'm really for. And every natural number is the sum of 4 binary palindromes, and the number is optimal. And binary palindromes are things that you learn in your theory of computation course. One of the exercises often is to show that can you recognize a word which is a palindrome, right? Where the word is equal to its reversal, and you reason about it with finite state automata. Then you go to push down automata, and this is the sort of exercises that you get in theory of computation, right? So, and this says that in fact, every natural number is the sum of 4 binary palindromes, and the number is optimal. Now, this is really what I'm pointing out is that it has opened up an exciting area of research. 2 years ago, Madhusudan, Rajshekharan, Novodka, and Charlotte proved that a version of the Waring problem, the Waring theorem, on binary. So in binaries, because so when you talk about it in terms of kth powers, right? In Waring problem, you talk about expressing numbers as the sums of kth powers, right? 3 cubes, 4 fourth powers, and so on. So kth powers. Now, what are kth powers in words? Well, W square is WW, right? W cube is WWW, and so on. So for kth powers of binary words, they again show something like a Waring generalization of a Waring problem in binary, and that's very recent. That is, I think, 2018. Yeah. So how did we get here, right? So how was it that 200 years of research in analytic number theory with amazing mathematical techniques, and then some very elementary techniques suddenly becomes possible, and you have this spate of additive bases that are showing up like every year, right? And this is all like 21st century research, right? So what is the key breakthrough? And I think that's what I want to emphasize in this talk. So this is where it starts. David Hilbert, and the famous statement of David Hilbert: "Wir müssen werden, wir werden wissen. Wir müssen wissen, wir werden wissen," as he says. So he says, we must know, we will know. And ironically, it was on 8 September 1930, Königsberg. And we started off with Hilbert's famous lecture in the Congress of Mathematicians in the year 1900, where he proposed 20 problems and 23 problems, sorry, and where it started off, as I said, mathematical logic as we know it today. And this was in 1930, when Hilbert had just retired, and he was asked to speak in Königsberg. It was in his honor, retirement. And there he says, there is no ignorabimus in mathematics. He says, any question in mathematics, we can answer. And that's his entire Hilbert program. And I have even the, Deutsche radio, the German radio actually broadcast excerpts from that. And I have actually the audio file if you want to hear Hilbert announcing this. He ends the speech, the entire talk, with this two words. And of course, it all started with Hilbert's dreams. He wanted to prove every mathematical statement, and that was killed conclusively by Gödel. He hoped for an algorithm to decide whether every statement had a proof or not. This is the Entscheidungs problem, Hilbert's very first problem, and this was killed by Alan Turing. That this is all impossible. But then the point is that in the process, as I said, from the ashes of the Hilbert's program rose mathematical logic as we know it today, and especially first-order theories of arithmetic. And it turns out that many first-order theories of arithmetic do admit such algorithms, where we can actually take statements of this kind, like I wrote, there exists x, there exists y, x plus y equals this, and yeah, and this. Um, so you can explore it in terms of abstract logics, and you do find decision procedures, and one of them is what I want to talk about today. Well, there is Gödel, and one of the well, Gödel showed that the first-order theory of arithmetic with addition and multiplication is undecidable, right? I mean, that was the major result of the Gödel's incompleteness theorem. Of course, he showed that any formal system that can encode addition and multiplication will always have some statements lying outside it. But in the process, he showed that first-order theory of arithmetic with addition and multiplication is undecidable. And then people were interested in finding out, okay, which are the arithmetical theories which are decidable? What if you have only addition? And this was shown by Presburger. Presburger is also a very, I would say, romantic figure in this. He lived for only 39 years, and he used Tarski's. No, Tarski proved that real arithmetic is decidable. That is, if you are not talking about on integers, but on natural numbers, but on the reals, it's decidable. And he came up with the theory of quantifier elimination, and this technique was extensively used. And Presburger used quantifier elimination to prove the sort of theory of natural numbers, addition being decidable. And interestingly, I mean, he was Tarski's student, and Presburger was actually quite heartbroken because Tarski felt that this result was good enough for a master's thesis, but not for a PhD. So he told, I mean, he got his master's, but Tarski said that you have more work to do, and started doing. And then the war, he went. And, he was, in fact, he died in the Holocaust. Yeah. Okay. So Buchy, who working in the 1960s, long after, showed that instead of quantifier elimination, you could use finite state automata to give a much simpler proof. And this is really the turning point that I want to talk about. And that makes a huge difference. Now, I have actually talked about it in earlier, Buchy's theorem, in other Calcutta Logic Circle meetings. In fact, I think almost exactly 2 years ago, when Sukanta organized his workshop in Howrah, I gave a bunch of lectures on Buchy's theorem, and I didn't talk about Presburger arithmetic there, but the idea is that you can use finite state automata to give proofs of questions of this kind. And well, here is Presburger. It's very young, as I said. Now, Presburger arithmetic, the kind of sentences that you are writing is that x is even, right, as there exists y, such that x is equals y plus y. How do you say x equals 1? Well, you say x is not equal to 0. 0 is definable because it's the minimal element. And then x is not equal to 0, and among all the other elements, this is the minimal element. Right? And addition is commutative. Very simple sentences I've written, but main point is that, order is definable once you have addition, and then you can ask a lot of questions. So what is Buchy's proof idea? So the idea is that you use automata to accept words over an alphabet, sigma kn, where k is the base. Without loss of generality, assume that base is 2, so that you are talking about binary. And then you can talk about n tuples of integers. That's because your formula can have n free variables, so you have to be looking at models with have in assignments. So for instance, suppose you have a formula with two free variables and you want to show that it's true at, x is 7 for x 17 and y is 5. Basically, you represent 17.5 by the word where you take the binary representation of 17, which is 10001, and 5, which is 00101. Note that I need padding, right? So that they're of equal length. And now, so you have taken it and talked about it in positions. So you see that in this word, the very first position is labeled by a bit sequence, right? Whatever base k sequence of. So it's an n-tuple in base k, right? So let's again k equal to 2. So it's a pair of bits, right? So you just, so the left components together give the first number and the right components together give the second number. So this is the representation. So in general, we are going to talk about any number, any natural number. When we talk about, the number is defined in terms of the bit sequence or whatever in base k. And the idea is that now you take your formula and you construct an automaton by induction on the structure of the formula. So you construct automata for checking atomic formulas and then use closure properties. Now, so, and I have written with finite sequences, finite words, and but Bucky's theorem takes with, so you want to look at, natural numbers. So you look at infinite sequences and arbitrarily long finite sequences as well as infinite sequences. And but for what we are talking about at this moment, it's enough to consider finite words, automata over finite words. And we know that automata over finite words, the languages accepted are closed under complementation, closed under Boolean operations and projection. So once you construct automata for the atomic formulas, the closure properties tell you that if I have an automaton for a formula alpha, I can construct an automaton for negation of alpha by complementation, right? How do you complement? Well, we know, what you will get are NFAs, and you do NFA complementation, which means you determinize it and complement the final state. And then once you have automata for alpha and once you have automata for beta, you can take language intersection, and again you can construct an automaton for intersection. So that will give you a conjunction. And existential quantifier is projection, and alphabetic projection is something that, again, regular languages are closed under. So you just have to construct automata for checking atomic formulas. Now, what kind of atomic formulas you've got here? Well, x equals y, right? The position x equals position y. The position x is less than position y. And then, importantly, addition, x plus y equals z, right? Now, notice that now at one position, you're going to have, suppose you're talking about, so you just have, uh, in the case of addition, right? You have three variables, you have 3 bits, right? You have 3 bits, and you're talking about adding 3-bit numbers, and this is something your automaton can check. Maybe what I can do is to try to draw an automaton for it and show you. Doing that, I have to stop share. Let me see if it gives me a board. I'm very bad at manipulating these things. I hope you won't. But once I can get a board. Oh, why does it give me a? What? Just one moment. Hold on. I will. Yeah, I'm trying to open a board. I hope it will work. Yeah. Okay. Now, let me again try. I don't know why it doesn't. Okay, let me try entire screen and then all visible windows will be shared. It says, okay, I'll try. Okay. Now let me see if it. So can you see my screen?
Yes, yes, yes. Yes. Oh.
And can you see my board?
Yes, yes,
I'm
yes.
not able to see it myself, so yeah. Okay, so I'll try to draw an automaton for addition, right? So basically you have, yeah. I'm not very good at this, as you can see. So you have two states, one for no carry. It's not writing well. Okay. And so once I have in no carry, remember I have 3 bits, right? So this is a self loop for, so I have 3 bits A plus A, B, C. Oh my God, this looks quite horrible. I'm sorry, it's okay. Okay, if there is, if A plus B equals C, it goes here. And once A plus B plus 1 equals C, it goes to the state with carry. And it keeps looping here for A plus B plus 1 equals C plus K. Remember, K is the base. And when it is A plus B equals C plus K, it loops back. I hope it makes sense. Huh? I should have just drawn it in the PDF function. I thought I would be able to draw properly, but okay. Let me. Yeah. I hope the automaton is clear. It's a very simple automaton, right? That it has got only 2 states from no carry to carry, and all you do is that, remember that the 3 bits, if when I add the first 2 bits and I see that adding 1 gives me the C, then I go over to carry. That is when I sense that that is a carry, and as long as A plus B plus 1 equals C plus K, I keep looping. And the moment A plus B is the same as C plus K, I come back. This is a simple enough automaton that recognizes that. So since you have brought it down to bitwise addition, with bounded memory, your automata can do. This is the main. And similar automata that you can write for x equals y, that's completely trivial. And x less than y, the idea is that the automaton simply guesses and keeps waiting. So it starts wait until it sees the exit position and then moves. And the moment it sees the second one as y, it says I have accepted, and it's a final state. So this okay. Yeah. Has it come back to my PDF? So are you seeing the PDF now?
Yeah.
It's okay? Yeah.
Yeah, it's okay.
Okay. So any question on this? This is the, I mean, of course, there are some details, but I hope the idea is clear how the automaton construction just goes inductively. Any questions, or shall I go ahead? Will I move on? Okay. Then, yeah. So once you have, this is Presburger arithmetic, right? Where you have the atomic formulas are x less than y, x plus y equals z, x equals y, and you have whatever predicates you have got. And now comes the question, how much more can you add, right? Remember, if I add multiplication it will become undecidable. So I can keep addition, and can I add some more? And Buki suggested that the function that you add is nu k of n, which is the exponent of the highest power of k dividing n. So this is, for instance, if I take 2 as the base, 2 power 3 divides 24, and that's the largest power. So nu 2 of 24 is 3. Turns out that actually he was wrong. The correct extension turns out to be vk of n, which is the highest power of k dividing n. So if you take 24, the highest power of 2 that divides 24 is 8. 2 power 3 is 8. So now, and this is a very nice theorem, that the theory of n plus addition, Presburger arithmetic extended with bk is decidable. And again, the proof is by construction of automata. This is a very nice proof, but I'm not going to take you even talk about it anymore. If somebody is interested, I can go over that. But the point is not so much that. Cobham's conjecture is that this is the borderline, right? In the sense that you add any more functions more powerful than this, it will become undecidable. Of course, we don't know. I mean, because that's a very loosely made statement. But you know, in the last 30, 40 years, people have been trying. I'll mention some other open problems towards the end. And what is very nice is that the main theorem says that a set of integers is definable in this theory if and only if its characteristic sequence is k automatic. Now, what is that? And that's what we are going to get into now. And so automatic sequences form the main idea and in this kind of proof. And as I said, those are the ones that have led to many of the breakthroughs that I mentioned earlier. So it's time to define automatic sequences and describe the connection to linear cellular automata. So what are automatic sequences? You say a word, now I'm talking about sigma omega, that means infinite sequences over a finite alphabet sigma. And so you say a sequence in sigma omega is an automatic sequence if it is generated by a finite state automaton with output. And the deal is that given a number n as input it should be, the automaton produces the nth term an as its output. So this is the idea. So take a word a1, a2, an, so on, and what the automaton will do is it recognizes that word, you say, and the idea is that. So again, once again, think of sigma as 0, 1. Think of it as a bit sequence, and now you have an infinite bit sequence. And the idea is that your automaton is it's an automaton with output, you see. And in this particular case, if you want 0, 1 sequence, then it's going to output elements, bits as output, and it gives you an infinite stream, and that's the idea. And so this is the definition of an automatic sequence, and we can talk, in general, it is base dependent, so we call it k automatic sequence. And once again, for practical purposes, for whatever we are saying, at least the examples, 2 will do. And here is a sequence, and it's a very famous sequence, the Thoe Morse sequence. It's a sequence obtained by starting with 0 and successively appending the Boolean complement of the sequence obtained thus far, right? So what does this mean? You start with 0, the next, so there is the first term of the sequence, second term is 1 because it's a complement. Now you take 0, 1, which is what you have got, and the next term is 1, 0, which is the complement of 0, 1. Now you've got 0, 1, 1, 0. The complement of that is, I'm sorry, I have put an extra 1 here. It should be 1, 0, 0, 1. Right? Now, what you've got so far is 0, 1, 1, 0, 1, 0, 0, 1. Complement of that will give you 1, 0, 0, 1, 0, 1, 1, 0, except for this 1, which is wrong here. That the highlighted one is wrong, and otherwise it's correct. So this sequence is you get this sequence. Yeah, I think I have actually written it correctly after that. So this is a single infinite sequence, and this is it has applications in partition theory, combinatorial game theory, fractals, resource allocation. I mean, it comes all over the place. I mean, it's a very famous sequence. And the automaton construction is extremely easy. You can give it by the alphabetic morphism. What's an alphabetic morphism? It takes elements of the alphabet and gives you strings over that alphabet, right? So, and it's given by the morphism. You map 0 to 0, 1 and 1 to 1, 0. Okay, I know this is grim, but let me actually try to draw the automaton again. If you will be patient with me, I'm sorry about this thing, but I hope. Yeah, let me try. I don't know how to do only that. It should be able to get the Jamboard, but I'm not able to get it. So I'll again show the entire screen and go over to Jamboard. Yeah, can you see the? Yeah, can you see the board?
Yes. Yeah. Yes.
Okay. So clear for me. Oh, okay. This is some internet. Okay. Just took time. Okay. So once again, the Thoe Morse sequence, what are we trying to do? You want to map 0 to 0, 1 and 1 to 0. So the automaton okay, so has two states, 0 and 1, and this is the initial state. And remember, there is no final state because it's just an infinite sequence, right? On from 0, there's the 0 outputting state, and this is the 1 outputting state. And on 1, you go from 0 to 1. After that, if you have a 0, you remain there. And when you get a 1, you have to output 0. So you come back. And as long as you're getting zeros, you again, it's fairly ridiculously simple automaton, right? And you can check that when it gets a 0, it's going to output a 0 and then go on a 1 to 1, right? And so it, the alphabetic morphism mapping 0 to 0, 1 and 1 to 0. Is it clear that this automaton? Instruction. Okay. Yeah, and so, and now this you can check that when I map 0 to 0, 1, you see you can get the first two elements, and then 1 to 1, 0, I get the next one, and then you keep getting complements because of that. And the way the morphism works is very nice because it does the concatenation for you and generates the sequence. Okay, so by the way, this business of automatic sequences is also takes you to some very interesting thing, because now you can look at real numbers, right? Because real numbers, you can think of them as in the k-adic, whatever base that you are looking at. For instance, in the case of infinite binary sequences, you have binary representation of real numbers, and so you can ask which irrational numbers are automatic, etc., etc. So there is a lot of very interesting research on characterization of are there transcendental numbers that are automatic, etc., etc. So that's a different direction, but I'm talking about something else. So another really beautiful sequence is the Fibonacci word, or the Fibonacci sequence. And the definition is exactly what you would expect. The first one is 0, the second one is 1, and then you just concatenate the previous two sequences. So that's the Fibonacci. So the idea is that rather than addition, because you're talking about words, you keep concatenating them. And the resulting infinite sequence is called the Fibonacci sequence. And the map for this is really straightforward. 0 is mapped to 0, 1, and 1 is mapped to 0. And you can check that when I start with 0, I get 0, 1. And then when I apply it again on 0, 1, remember that 0 will map to 0, 1 will map. And so this will map to 0, 1, and 1 will map to 0. So I get 0, 1, 0. And then once again, I apply sigma to that. Here, the first one will generate a 0, 1. This will generate a 0. So I've got 0, 1, 0. And the last 0 generates a 0, 1, and so on. Now, and already I'm sure people are able to see cellular automata that generate many of these kind of automatic sequences. These morphisms are, of course, these are finite state mechanisms, so it's not very surprising. But characterizing exactly which class generates any of these is what is very interesting. And you keep doing that, and the fixed point of this sequence of sequence sigma n is in fact the infinite Fibonacci sequence, and that's one particular sequence. And so the morphism actually gives you the automaton. I'm not going to try to draw it anymore because you can see that I'm very bad at it. But it's very, very simple. Once you have this, once you have an alphabetic morphism, drawing the automaton is completely straightforward. So there is a very rich theory of automatic sequences. They appear in many areas of mathematics, theoretical computer science, and theoretical physics. It gives you a non-trivial class of self-similar sequences. And they're, in a mathematical sense, between periodic sequences and chaotic sequences. And they're invariant under many interesting transformations, shifts, and invariant under shifts, invariant under block compression, invariant under linearly indexed subsequences, and many. And okay, this takes us naturally to von Neumann. And because it's clear that when you're talking about double sequences, k-tuples of automatic sequences in base k, it's very easy to see how cellular automata, evolutions of cellular automata would generate these. And that's really the connection that I'm talking about. And so now I'm not going to say what cellular automata are to this audience, but the formalism that I want to refer to and use is basically you'd have a lattice, z to the d, each vertex in a cell, and you have a finite neighborhood of sites for each element, and you choose the Moore neighborhood or the von Neumann neighborhood, and you have a finite set of states, and you have a transition function from Q to V to Q. So from, for every cell, looking at the state of the neighbors, you move to the new state. And to each element I assign an element xi as state. And you start with the initial configuration that tells you for each element what is the state that is assigned. And then you keep repeatedly applying the function f from C0 to beta C1. Cn plus 1 is f to the n C0. And it's not accidental that I use this notation to talk about alphabetic morphisms, and I'm using the same. So it's the same idea, and this is the connection that will take us. So of course, you have parallel updates, and when d equal to 1, we draw two-dimensional patterns, and that gives you the temporal evolution. Now, in the case of linear cellular automata, you're talking about values taken in z/dz, the ring of integers modulo d, and the transition rules are linear. Now, consider the LCA generated by the Pascal's triangle rule. Right? This is the double sequence UMN, which is nothing but M choose N mod D, right? And this will give you the Sierpinski triangle modulo D up to rotation. And the theorem says that this sequence is P automatic if and only if D equals a prime power P to the K. Equals some prime power, and it's in fact that. So this is a difficult theorem. I can take you through the, as I said, there is no hope of my drawing the pictures, but what I can show you is from the paper, the way the generation is done. But maybe in the discussion I can show you how the generation is done. But this is not an easy theorem. This is a difficult theorem to prove, and but this already tells you that in the particular case of these coefficients, right, M choose N, in when you have mod prime power, right, when you have your sequences where the coefficients are modulo of prime power, then in that case actually this automatic. But the moment you say it's automatic, it means that remember the old Yuhi-Breuer theorem that tells you that they are actually definable in Presburger arithmetic, right? So in the particular case where the temporal revolution happens to be, right, of the form where the coefficients are M choose N mod a prime power, you can actually describe them in Presburger arithmetic, and in fact you get a decision procedure. Right? That is the kind of payoff that you get in this. As I said, I'll go over the paper for Alouche et al. To show their generation. But the general question is, when are double sequences generated by LCAs automatic, right? So at least in the case of binomial coefficients, they solve the problem completely and show you that the if and only if characterization condition. And so for one subclass of LCAs, when you look at the temporal evolution, you can write many properties and check automatically. There is an algorithm to check whether the temporal evolution of these automata satisfies certain conditions. The general case is very difficult, and turns out it relates to the question of how to characterize the self-similarity exhibited by evolution patterns generated by linear cellular automata. This is a very, very nice problem. Formally, one can define and take it, but the point is that this is a hard question, and this is one of the partial answers that people have done. So I would like to first finish off what I want to say, and then maybe take up the Alouche paper, depending on interest. This is really not my work anyway. So the point is that because this gives us hope for a first-order theory of evolution patterns of LCAs, and it is clear that Presburger arithmetic is not enough. We have to add something to it. What exactly we have to add is not clear. And so Presburger arithmetic suggests that the search for closure properties and invariance under transformations, right? That for automatic sequences, a lot is known, a lot is open. I'll mention some of them in the next slide. So the point is, the moment you can get any kind of characterization showing that for this particular subclass of at least in the case of linear cellular automata, if you can show when they give rise to automatic sequences, you have access to decision procedures. In fact, you can use tools, existing tools such as Walnut, to actually decide these automatically. And this is something that has been done by the group, the Walnut group. I think it's people in Switzerland who have already put out a lot of results of this kind. And there are many open problems. The very, very nice logical questions to answer is the theory of Presburger arithmetic extended with P2, P3, right? Power of 2, power of 3. Not just power of 2, right? But also power of 3. Is it decidable? That's open. If I add a primes predicate, x prime x is that x is a prime number. Is that decidable? That's a beautiful open problem which has been there for since 1940. Tarski posed these things. The theory of Presburger arithmetic extended with the Euler function, is it decidable? We don't know many of these things, but the point is that for the theories, especially when you extend with prime numbers, when you extend with Euler functions, a lot is known about the automatic sequences that you get in these by, you take these morphisms that you define and keep on taking their iteration and look at the fixed point that is generated and look at the automatic sequences. A lot is known about the mathematical structure of these, but as I said, the general decidability question is open. But like I said, in the last 5-6 years, there are so many results that are coming out. I mean, generally in the last 2 decades, there has been so much very impressive progress on these. I don't know whether these particular questions will be tractable or not, but there certainly is a lot of hope for deciding properties of huge classes of automatic sequences right now. Okay, so this is all that in this broad outline that I can give. And as I said, I can go over the Alosh paper if somebody is interested. But before that, probably I would like to have some discussion on the broad ideas that I am presenting. Thank you.
Hello. Hello, may I ask one question,
yes,
please?
Yeah, of course. Yeah.
Hello. Okay. So, in the first part of your lecture, that which numbers are can be recognized, and in that way, in the last part, in the fragment, you talked about the undecidability of the prime numbers, being prime numbers. I was just wondering whether prime numbers, any relation you have in your memory with regards to prime numbers in terms of 0 and 1s, any kind of limited results?
No.
I'm just asking over because because of the Goldberg conjecture, I was investing some time.
Okay.
Yes,
so,
that's why related with prime numbers. Yes. Similar to Wood's number, any relation with prime numbers?
Okay. No. Of course, there is relation to prime numbers. The main idea is that now you have primes available as an atomic predicate for you, right? You can write formulas like x is prime and y plus z is this, then etc., right? It's what you are doing is lifting whatever you've got in additive number theory with primes as thrown in for you in your set, right? Remember the general question in additive number theory that I started with. You have set of natural numbers and you have some arbitrary subset S, right? 0 belongs to S, right? Now, what we are now saying is that the set S that you are going to look at has primes available to you, right? Now, using this, what kind of basis that you can form? That's one kind of questions. Here, the algorithmic question is that if I write any formula, any property, right, where you are able to talk about, for instance, let's say that in the context of this iterations, right, you are able to also, say that at this stage I will get something, prime power, for instance, right? So now, can I use that to describe some properties of the sequences that I want and have an algorithm to check whether the property holds or not? That's open. I didn't say it's undecidable. I said it's open. We don't know whether it's decidable or not. Yeah.
And regarding Goldberg conjecture, any advancement in your?
No, come on. No, not at all. Not at all. I mean, let's say, this line of these results that I'm talking about are not answering open problems in number theory. That's clear. But what they are doing is to ask questions which number theorists have not asked before, right? For instance, many questions on periodic numbers, right? Now, you're able to ask an answer. And what is amazing is that many of these in binary, like I said, binary palindromes, right? And binary squares, right? That when you take binary k powers, you have a version of Waring problem. Now, this is something that never occurred to mathematicians, right? My point is that they are answered, and they are answered by elementary means, right? I mean, it is not deep mathematics, right? Once you understand the principles, and I mean, you have to learn a bit of logic and automata theory, but once you learn that, the proofs are eminently accessible. They're very simple. They're very compositional. They have a very nice structure. So that's all that. It's not that you are using these kind of theory to answer deep mathematical open problems. No, I don't think that's likely. But you can ask new questions, right? And they are very interesting too. And especially on self-similarity, fractals, and so on. So that's why I said, these are somewhere between periodic ones and the chaotic ones. So, and so a lot of very interesting structures I mentioned.
Okay. Anyone? Any question? Yeah, sir.
Yeah, may I ask,
Yes, please.
Jam, as usual, I enjoyed so much. So many thought-provoking things. So I have just, one query or maybe suggestion. So you're talking about theorem of sequence, right? And then you talked about LCL, linear cellular, I mean the cellular automata, one-dimensional cellular automata. So any relation, any suggestion that the relation between, have you any kind of relation between these two, or can you do you think that the cellular automata can generate this kind of sequence?
Yeah, so I am saying linear cellular automata, right? That's all I'm talking about. And within them, I mean, the point is that linear cellular automata are already Turing complete. Okay, so in general, if I take an arbitrary linear cellular automaton and want to look at its temporal evolution, I mean, will it reach a fixed point, right? I mean, this is an undecidable problem. There's no question at all, right? So the question is, when is it that, you might want to ask a question, when is it eventually periodic, right? When is it, what is the period? Can you compute the period? Now, these kind of questions may be decidable, not for arbitrary linear cellular automata, but for linear cellular automata generated by some subclasses of rules, some rules, right? Which ones we don't know, right? And that's the real interesting research question. But the point is that the Pascal's triangle rule is something very simple, right? Now that you can do. Now, so at least a few of them, right? The ones that where the coefficients are binomial, it's clear that the answer is, I mean, they are decidable, right? And so there are uniform algorithms that will give you. So the main point is that to analyze these in general, you don't have to come up with one technique each time, right? You will be able to get a uniform result for a whole subclass of LCA. Here is one. Are there more? Is the question. I mean, of course there are more. There is no question. There are more. I mean, binomial coefficients is just one case, right? So probably there are lots more of that kind. And which are the ones? And how much more can you add and get decided? That's the interesting question. So the point is that if something as simple as one-dimensional cellular automata with linear rules, right? There are a whole lot of algorithmic questions that have not been answered, right? That surprisingly, right, is what the focus is on, and it's very likely that once we manage to answer questions like I said in 2 dimensions, right? Probably, like I was pointing out, a spate of results relating additive number theory and these. Once somebody starts showing the way, people start producing many papers, right? So I consider this Alush paper, which relates these two, the complete solution for binomial coefficients as a kind of a breakthrough, right? Now, if we understand these techniques, probably we can add more, and and very quickly, many people working on it start finding many interesting characterizations. That's the hope. I mean, like I said, it's all speculative. I have no. These are not my theorems anyway, right? I mean, these are
Which one?
the Alush paper, the theorem that I mentioned, that the binomial coefficients, when they are prime powers, that's exactly when you get automatic sequences. In the case of one dimension and linear rules. So that's a. I'll mail you the paper. And
Yeah,
Jam,
very nice. Very.
Can you please show us that proof you are talking, that you will be showing us that
I
proof?
can, I can. Just one moment. As I said, I'm unable to. Just one moment. Yeah, so I can show you the paper itself, and this is a paper in discrete applied mathematics. And so this gives you the pictures will show you how the generation. So here is the automaton, right? The two-dimensional. See, the automata for most of these are very simple. First, to tell you that for binomial coefficients, that generating the Lucas formula is something very straightforward. And it's not. And here are the two-dimensional automata for the Comer formula, but I am more interested in showing you the, yeah, where are the LCAs? Yeah. So here is a look at the generating polynomial 1 plus x squared mod 2. Yeah, can you see the figure? Is it visible or?
Yeah.
Okay. And this is the Pascal's triangle one with this. And now you can see with 1 plus x mod 4, you can see how the structure changes, right? So that's why I said it's a matter of characterizing this self-similarity. And that's the rescaled evolution. Now for this is 1 plus x mod 6. And what is very nice is, look at this little remark, and that already shows you the proof technique, right? So this is in fact a union of the evolution sets of 1 plus x mod 2 and 1 plus x mod 3, giving you 1 plus x mod 6 here. And now, when I look at 1 plus x mod 6, right, this is the, you get this here. And what they're able to show is this, precisely this evolution is given by this morphism. You remember the kind of morphisms I was showing, right? With 0 mapping to 0, 1, 1 to 1, 0, etc. Now, of course, here the morphisms are slightly more complicated because you have to do it on 2 dimensions. I was just doing it on 1 dimension at that point, right? Because yeah. So here is there are 4 states, and its coefficients modulo 4 is shown here. And from that, you can generate for the general K-tuple case. This is only to give you the idea. The proof is fairly complicated. I mean, it's, yeah. My point is that you can define morphisms in a very similar fashion to what I was talking about on the sequences there. That and the morphisms actually, once you, as I said, you look at the picture, get the idea, the morphisms are easy, and draw, the coming up with the finite state automaton from the morphisms is something completely straightforward. The final proof showing that this is, this basically says that you can use an automatic sequence to generate that pattern. That part is easy. Yeah. Only if part, the other way, that every such evolution is automatic. That is not easy. And that is, serious mathematics involved. But that is not surprising, right? I mean, when you are looking at evolution of cellular automata, describing the evolution is very easy. To show that every such evolution has this property, or every rule will, even if it's, the other direction is always hard. So that is the characterization part. But I mean, again, this would be at least one full talk in itself to present the results. And there's no way I can do it without a board. I wouldn't even dare to try. Because this is not the sort of thing one can do in PDF and stuff like that. Actually, I intended to do that, but I realized that I'm terrible at using this. So if I had a board, I would just go to the board and start doing it. So.
Okay. So anyone else having any other questions?
Yeah, if I come to Shibpur sometime, I will do the complete proof, I guarantee.
Yeah, but we will miss that. So, yeah, now we are not a Shibpur.
I know, I'll do that in Trichy for you. No problem.
Okay.
Maybe.
As I said, I'm sorry that it was mostly on topic that was not very much cellular automata. I mean, I like this topic very much, and this logic automata connection, I think, is really deep.
No, it was very much interesting and thought-provoking. There is no doubt in that.
So that result, the warring problem done in binary, and that they have proved 2 years ago, is by Madhusudan, Yonotka, and Charlotte. And Madhusudan is a former student of mine from IMSC. So he's been in Chicago for some time, and he's one of the authors. So, yeah. And we would have never dreamed that somebody who comes with an automata theory, logic background, can solve a problem in additive number theory, right? I mean, something like a warring problem. It's like extremely nice.
Thank you, Jam, for your support and for coming over here and giving this nice talk. Monica, then if nobody, if no question is there, then you may conclude.
Yeah, okay. So if no other question is there, then I want to thank Jam for
Yeah.
coming here and giving us that beautiful presentation. And I surely want him to be on before the board and doing all those calculations.
Right.
It's very beautiful to see.
Absolutely.
Yeah, yeah. That I'm missing right now. So I hope in near future we can do that.
I will do, certainly. Yeah.
Yeah. And we can recall his class a few years back. He was referring to. So, Jam, you're referring to this, 2 years back, you told me at the school. It's so nice.
Thank you very much. Thank you. Okay, then. Bye bye.
Thank you.
Thank you. Nice seeing you all.
Bye.
Okay. Thank you so much.
Okay.
So I've already announced for the next webinar, that is on 9th of January. So please join us on that webinar. Thank you for coming. Have a nice time.